Hello people, this is Calculus 1, Chapter 4, Applications of the Derivative, and we are studying from Calculus Early Transcendentals by James Stewart, and this is Newton's method. What is Newton's method good for? It's good for approximating the zeros of a function. So we are trying to find f of x equal to 0, solve for x. It's also good for solving equations that are really difficult to solve, as like an example, solve cosine x equal to x. That's a really difficult thing to do, but we could move both terms over to the other side, cosine x equal to 0, and we could name our function cosine x minus x equal to 0 and consider that for our approximation techniques. So it's a pretty decent application to consider when you are trying to solve equations and when you're trying to find roots. All right, so how do we do this? Well, just the geometry of this here, if we take this graph in blue before you, our f of x, we're going to be using the most important concept of Calculus 1, which is the equation of the tangent line. And what is that good for? It's a really good approximation to the curve at that particular point. So we can consider using, if we zoom in on the equation of the tangent line very, very closely, for values really close to a particular point, that equation of the tangent line at that point, we can consider using the line and work with the line instead of the actual graph, and we can manipulate, find zeros, and whatnot. So that's what we do here. So we first start with a first approximation to the zero. So we're really on a mission to where r here in this picture is really the root of the equation. That's r is going to be the value of x where f of x is equal to 0, right? Because the output there is 0. So sometimes we do want to consider using graphing calculators to find our first approximation and then get more accurate approximations by using Newton's method. So how do we find the equation of a tangent line? We find the equation of a tangent line by first taking the derivative of our function and evaluating the function at the point very close to, or at the point x1. So we first pick our first guess at a root for our equation, something that might be close to the root. Sometimes we might want to use a graphing calculator to get a first approximation. So we start with that value x sub 1. And of course, f of x sub 1 would be the y output for our function, and this would be our x1, y1 in the equation of the tangent line. And we know that f prime of x sub 1 would be the slope. So if we were to start with our very first tangent line of y minus f of x equal to f prime of x sub 1 times x minus 1, or x minus x sub 1, then we would want to find the x-intercept of this line. And that x-intercept would be our next x sub 2, our next approximation. So if we find the x-intercept of this line and set that equal to x sub 2, which would be our next root, right? Because, again, the equation of the tangent line at x1 is a nice approximation to our curve, and if it's a nice approximation to our curve, then the x-intercept of that line is going to be a nice approximation for our root. And so that's what we do. So again, since our x sub 2 is going to be our next root approximation, we would use that, and it's on our line, so we can take that point and put it into the equation of our tangent line. So we would be substituting our y value and substituting our x value. So down here we would substitute y would be our output and x2 would be our input. And now we can actually solve for x2. So if we're going to solve for x2 here, clearly we can divide on both sides by f prime of x. And so we would have f of x1 divided by f prime of x1. And that's going to actually equal x2 minus x1. And then that's going to imply if I added x1 to both sides, I would get that x2 is going to equal x1 minus f of x1 over f prime of x1, right? So we then want to continue in doing that. We want to repeat that process again. We want to go, okay, x2 is our new approximation, so let's find the equation of the tangent line of x2. And finding the equation line of x2, we would have x2, f of x2 is our point. We would have our slope equal to f prime of x2, and we'd begin again. Then our y minus y1 equal to m times x minus x1, and really in this case 2, right? We would have this tangent would be y minus f of x2 equal to f prime of x2 times x minus x2, and x-intercept would be the next approximation, would be x3 comma 0, right? Your x-intercept is when y is equal to 0. It would be on this line. And so we would plug those values in. We would have 0 minus f of x2 equal to f prime of x2 times, and our x3 here minus x2. And now we would solve for x3 to get our new approximation for our 0. Okay, so in dividing both sides by f prime of x2, we would get x3 minus x2, and in solving for x3, we would get adding x2 to both sides. So x2 adding to that side would be positive, and we'd get f of x2 over f prime of x2. So in general, we can move towards and we would repeat the process again. So it's kind of like we would be doing this, going up, and we would be taking another tangent line, right? And eventually we would get really close to our 0. And what's important here in Newton's method is to pick a relatively good guess. Because if you don't pick a relatively good guess, then you could end up with an endless spiral where you're not really, pun intended, zeroing in on the actual root, okay? But you can tell from here, if I did do that slope of that tangent line, this would be my x sub 3, and look at how I'm getting really close, and I would be doing that once again. I would be going up to the curve, finding its equation of the tangent line, right? And you can see where maybe it might take 10 steps, it might take 3 steps, it might take 2 steps, but the more iterations you make, the closer and closer you should get to your root. Okay, so it might be worth it to now look at an example of how you would find this. So really, in general, your Newton's method to approximate the root of a function, i.e. f of x equal to 0, is if you start with x sub 0, or start with x sub 1, really, then as the first guess, then x sub n plus 1, your next one, is going to be the previous one, take away f of x sub the previous one over f prime of the previous one. So instead of using your hand calculator, I often advise students to use Microsoft Excel. So in this next example, as an example, I'm going to show you how to walk through Microsoft Excel in order to use Newton's method to come up with your approximation, so that it doesn't take you a lot of time to plug in and evaluate the functions at particular points. You can just spend 10 minutes to program Excel, and you can do as many steps of Newton's method as you would like. Or, you can do them by hand as well. But let's say, for instance, we want to find an approximation for the square root of 2, okay, using Newton's method. So we know that x squared equal to 2. Our solution would be x equal to plus or minus the square root of 2, and so in reality the square root of 2 we can use as that as one of them. But if I'm actually solving this equation, and Newton's method is used to find roots of equations, I can always move all of the terms to one side. So I can say x squared minus 2 is equal to 0, right? And now I can say find the root of f of x equal to x squared minus 2, right? Because if I'm saying find the root of x squared minus 2, I'm asking, in other words, f of x equal to 0, right? So if I can always solve an equation and move all of the terms to one side, set it equal to 0, and then use that as my function, right? So this would be my f of x, right? And we would have that x equal to 0. So now I'm going to stop here, and I'm going to go and open up my Excel file. And I should have it in my Google Drive, but maybe I have it in the Google Sheets. I'm on Newton's method example, and I've done this already. So I just want to open it up for you to see. So I tend to build a column of x sub n, and then I build a column of f of x equal to x squared minus 2, or whatever your function is that you're trying to find the root of. Then I'm going to take the derivative f of x, f prime of x, and take that. Yeah, I know that that derivative for x squared minus 2 is going to be 2x. And then I'm going to find the calculation. I'm going to calculate the x sub n plus 1, and notice here that it is going to equal x sub n minus f of x over f prime of x. So I'm thinking, okay, what number is close to the square root of 2? I know that the square root of 1 is 1. I know that the square root of 4 is 2. So I'm pretty sure that the square root of 2 is going to be between 1 and 2. So I'm just going to start with 1. So that's what I do, and I start with 1. Then in this column, I'm actually going to plug in a formula. I'm going to use the powers of Excel to calculate for me instead of having the calculator. And so notice down here in the bottom, down below, down below I can see that I used to insert a formula. You always start with the equal sign, and I want to have that equal sign be whatever this value is here. So I want to say equals A6, because that's my column, that's my cell number. So equals A6 raised to the second power, and then subtract 2. In the next column, I want to take the f prime, and I know that f prime of xn is going to be 2 times x, because the square x squared minus 2, the derivative is 2x. So I'm going to say that that's going to equal 2 times, and then I'm going to click back to A6. So that's what that formula is, and we want to see in the lower column of your screen here, you see the formula that I used in there. And then I'm going to use another column that's going to give me what is my next approximation for the 0. And I want to say that that's going to equal the A6 and then I'm going to say it's going to be minus, and since I've already calculated the two numbers that is the division, I'm just going to say minus the B6 divided by the C6, right? So, and so now, what am I going to put here? That's going to be my next x2, right? This is my x sub 1, and the next row is going to be my x sub 2. So whatever this item is, or this calculation is going to be my next approximation so that I can begin again. So I just say it's going to equal that D6. Good? And so then I do the process again, but once I set those 5 cells together, now I can actually select these 3 and copy. Like I can copy that through, right? I copy and then paste in the other cells and they propagate. So again, we can continue, and you can see if I do just that copy paste in there. And since I'm on an iPad, it's kind of hard for me to copy and paste when I see that. Well, I guess, could I? I can say copy and then paste down here, right? Or I can just say paste, and it will just copy through. But notice here that if I just copy all of those cells down below, the formulas copy through and they propagate. And notice here that I'm starting to zero in on the same number. So it looks like I don't need to go much more than 3 steps to zero in on something that is the real root. And we all know if you plug in the square root of 2 on a calculator, you're going to get the square root. You're going to get 1.414 ... Good. So I just wanted to, show you a nice way to use the Excel to make those calculations and to demonstrate that using Newton's method is an iterative process. You want to do it a couple times to get a certain accuracy, and you know when to stop Newton's method is when you start getting the same decimal points in each iteration. That's it. Hope this was helpful for you, and I will see you next time for antiderivatives.